Okay, so today we are talking about 8.5, which has to do with something called rationalizing. And that is essentially getting rid of a square root in either the numerator or a denominator of an expression. Okay, so rationalizing denominators is what we are going to begin with. Oftentimes in mathematics, it is useful for us to rewrite radical expressions without the radical in the numerator/denominator. The process of writing an equivalent radical expression without a radical in the denominator is called rationalizing the denominator. And in order to rationalize an expression, we essentially multiply by 1. So, for example, rationalize the denominator of each expression. First up, we have 2 divided by the 2 over square root of 5. So I'm going to scroll down so I have a little bit of space here. So I'm going to write 2 over the square root of 5. And in order to rationalize it, we are going to multiply by 1, right? So we know that we could rewrite things that are equivalent as something over itself, right? So like 3 over 3 is equivalent to 1. Same thing applies when we are rationalizing. Square root of 5 over square root of 5 is in fact equivalent to 1, okay? So we have 2 over square root of 5. And in order to rationalize, but not actually change our expression, we're going to multiply by square root of 5 over square root of 5. Okay, and then we know that our numerator is going to be 2 times the square root of 5, and our denominator is going to be the square root of 5 times the square root of 5, and we can use our product rule for radicals right there. So square root of 5 times square root of 5, that's going to be equal to the square root of 5 times 5, which is 25, and then the square root of 25 is itself 5. So we will have 2 square root of 5 over 5. And that is the rationalized version of 2 over square root of 5. It's literally the same expression, except for now we don't have a radical in our denominator anymore. Let's do another example. So we have 2 square root of 16 over the square root of 9x. First thing we want to do is simplify that 2 square root of 16. So we know that's going to be equal to 2 times 4 over square root of 9x. So we have 8 over the square root of 9x. But then actually we notice that that 9 in the denominator is a perfect square. So let's break that up into square root of 9 times square root of x. So we have 8 over 3 square root of x. So first thing we do is we want to simplify that expression. And then we want to go ahead and multiply by the square root of x. So we don't have to multiply by 3 square root of x. We just have to multiply by square root of x. So we'll have 8 over 3 square root of x times square root of x over square root of x. That gives me 8 square root of x over 3 square root of x times square root of x. I know that square root of x times square root of x is equal to square root of x squared, and that the square root of x squared is x. So my final answer would be 8 square root of x over 3x. And again, no radical in my denominator, just as I was hoping. All right, next up, we have the cube root of 1/2. We're going to break that up using the quotient rule. So we'll have the cube root of 1 over the cube root of 2. The cube root of 1 is 1, so we're going to have 1 over the cube root of 2. And now we want to rationalize our denominator. Since the cube root of 2 is a cube root, we want to multiply by a value that will make the radicand 2. So our radicand is 2, but we want that 2 to become a perfect cube. And so if we multiply the cube root of 2 by the cube root of 4, then we will get the cube root of 8. And is the cube root of 8 a perfect cube? Yes. Okay, so we want to get 2 to 8, which is the next perfect cube. So in order to do that, we're going to have 1 over the cube root of 2 times the cube root of 4 over the cube root of 4. That's going to get me in my numerator the cube root of 4, and in my denominator the cube root of 2 times 4, which is the cube root of 8. The cube root of 8 is 2, and so I'm going to get the cube root, oh, wrong number. I'm going to get the cube root of 4 over 2. I have no radical in my denominator anymore, just as I had hoped. Okay, so when it's a cube root, you want to take whatever number is your radicand, so in this case it was a 2, and think about what can I multiply 2 by to get to the next closest perfect cube. Okay, so again, my perfect cubes are 1, 8, 27, 64, etc. So you want to take whatever is in your radical and think about how can I get it up to that next perfect cube? What can I multiply by? And so 8, we know 2 divides evenly into 8. And further, that 2 times 4 is equal to 8. So we can multiply by the cube root of 4 to get us the cube root of 8, which is 2. Okay, so take a second, think about that. That one's a little bit tricky. All right, next up, we have the square root of 7x over 3y. First thing we're going to do is use the quotient rule, which will give us the square root of 7x over the square root of 3y. Neither of those expressions can be broken down any further. And so we want to multiply by essentially 1, which would be 3y over 3y, square root of 3y over the square root of 3y. So in my numerator, I have square root of 7x times the square root of 3y times square root of 3y times the square root of 3y. That's going to give me 21xy, the square root of 21xy, times the square root of 3y times the square root of 3y would be the square root of 9y squared. And I know the square root of 9y squared is going to be 3y. So I'm going to get the square root of 21xy divided by 3y as my final answer for number 4. And again, no radical in my denominator, just as I'd hoped. No, I don't know what that noise was. I was going to say then and next at the same time. It didn't really work though. Next up, we have the 4th root of x over the 4th root of 81 y to the 5th. Okay, so first we want to simplify each radical if possible. Okay, so looking at our numerator, we're going to actually end up using the product rule in our denominator. So numerator doesn't really do anything. We can't simplify the 4th root of x at all. But, so 4th root of x stays. But in our denominator, we can think about this as the 4th root of 81 y to the 4th, which will have a perfect 4th root, times the 4th root of y, which will be left. So then I know that my expression simplified is the 4th root of x over the 4th root of 81 y to the 4th. The 4th root of 81 is 3. The 4th root of y to the 4th is y. So I will have 3y times the 4th root of y. And then in order to rationalize this expression, I can multiply my numerator and my denominator by, again, just the root in my denominator. So I can multiply by the 4th root of y over the 4th root of y. So in my numerator, I am going to get, actually, I did this, I think I made a mistake somewhere. Y to the 5th, y to the 4th, the 4th root of y, 3y times the 4th root of y. Oh, I want to multiply by something that will get me a perfect 4th root, right? Because I want to actually eliminate that 4th root in my denominator. And so in order to get y to the 1 to a perfect 4th root, I'm going to need to multiply the 4th by the 4th root of y cubed. The 4th root of y cubed. So my numerator, I'm going to get the 4th root of xy cubed. And in my denominator, I am going to get 3y times the 4th root of y times the 4th root of y cubed. So let's look at that denominator. We have the 4th root of y times the 4th root of y cubed, which is going to give me the 4th root of y to the 4th, which is equal to just y. So then I will have, I'm running out of space, so I'm going to go over here. The 4th root of xy cubed over 3y times this expression right here simplified to just y, so 3y times y, which is equal to y squared. So I'm going to get the 4th root of xy cubed over 3y squared. So that would be my final answer, again, without a radical in the denominator. And in order to eliminate that radical from the denominator, I needed to go ahead and multiply by the 4th root of y cubed so that this 4th root of y became the 4th root of y to the 4th, which has an even 4th root of just y. Okay, so this one's a little bit complex. Take a second and think about it. And we will move on to rationalizing denominators having two terms. So in order to do this, we need to recall that a plus b times a minus b is equal to a squared minus b squared. And these expressions, a plus b and a minus b, are conjugates of each other. So conjugates are essentially when you have something plus another thing or something minus another thing, and then the conjugate expression is the flipped sign. So if you had, for example, square root of a minus square root of b, the conjugate would be square root of a plus the square root of b. If you had x plus the square root of y, the conjugate would be x minus square root of y. Okay, and this is the key to rationalizing expressions that have more than one term in our denominator. We use the conjugate. So let's do an example. So we have 5 over square root of 3 minus 2. And in order to rationalize a denominator that has more than one term, we multiply by the conjugate. So we have 3 square root of 2 in, oh, I wrote that wrong. I wrote that problem wrong. This is supposed to be 3 square root of 2 plus 4. Oopsies. I am going to pause this video really quickly and fix these problems. Okay, now our problems are fixed. So first up, we have 2 over 3 square root of 2 plus 4. And so the conjugate of our denominator is going to be 3 square root of 2 minus 4. So we are going to multiply by 1 again, which is going to be 3 square root of 2 minus 4 over 3 square root of 2 minus 4. And that would give me 2 times 3 square root of 2 minus 4 in my numerator, and in my denominator, 3 square root of 2 plus 4 times 3 square root of 2 minus 4 in my denominator, okay? And then in my numerator, I still have 2 times 3 square root of 2 minus 4. And in my denominator, I'm going to use that property of a plus b times a minus b equals a squared minus b squared. In this case, my a is 3 square root of 2. So I'm going to have 3 square root of 2 squared minus my b is 4. So minus 4 squared. So then in my numerator, I'm going to have 2 times 3 square root of 2 minus 4, still haven't simplified that. And then 3 square root of 2 times 3 square root of 2 is going to give me 9 square root of 4, which is equal to 9 times 2, which is equal to 18. So 18 minus 4 squared is 16. So 18 minus 16. And then I have 2 times 3 square root of 2 minus 4 over 2. And I can see, oh, look, these 2's are going to cancel because, again, I have multiplication in my numerator, and multiplication allows me to cancel. So my final answer is just going to be 3 square root of 2 minus 4. Bada bing, bada boom. Let's do another example. So we have square root of 6 plus 2 over square root of 5 minus square root of 3. So if my denominator is square root of 5 minus square root of 3, then my conjugate is going to be square root of 5 plus square root of 3. Okay, and so now I'm going to have to do some FOIL action because I'm going to have in my numerator square root of 6 plus 2 times square root of 5 plus square root of 3. And then in my denominator, I have square root of 5 minus square root of 3 times square root of 5 plus square root of 3. Okay, so let's look at our numerator and let's FOIL that out over here. We have square root of 6 plus 2 times square root of 5 plus square root of 3. So square root of 6 times square root of 5 plus square root of 6 times square root of 3 plus 2 square root of 5 plus 2 square root of 3. Okay, and then square root of 6 times square root of 5 is going to give me square root of 30 plus square root of 18 plus 2 square root of 5 plus 2 square root of 3. So that's going to be the FOILed out version of my numerator. Then in my denominator, I know that I have a squared minus b, or a minus b times a plus b, which is going to give me a squared plus b squared. My a is square root of 5, my b is square root of 3. So I'm going to have square root of 5 squared minus square root of 3 squared. So that would be 5 minus 3. Because again, if you look at, you can do the math there, or you can think, okay, if I'm squaring the square root of something, those are just going to cancel and I'm going to be left with my number. So my denominator is just 5 minus 3, which is 2. So then if I go back to this problem, my numerator ended up square root of 30 plus square root of 18 plus 2 square root of 5 plus 2 square root of 3 all over denominator of 2. And there's nothing more I could do with that. I can't add any of the radicals in my numerator, and my denominator no longer has a radical, which is ultimately the main goal here. Next up, we have 2 square root of m over 3 square root of x plus square root of m. So again, I'm going to multiply by my conjugate, which is going to be 3 square root of x minus square root of m. 3 square root of x minus square root of m. So my numerator, I'll have 2 square root of m times 3 square root of x minus square root of m. In my denominator, I'm going to have 3 square root of x plus square root of m times 3 square root of x minus square root of m. And then I'm going to think about what I'm going to have in my numerator and my denominator. So if I distribute out my numerator, I know that I'm going to have 2 square root of m times 3 square root of x. That is going to give me 6 square root of mx. And then 2 square root of m minus or times negative square root of m is going to give me minus 2 square root of m squared. That square root of m squared is equal to m. So I'm just going to have 6 square root of mx minus 2m in my numerator. And then my denominator, again, is going to follow that a plus b times a minus b equals a squared minus b squared property. So it's going to be 3 square root of x squared minus square root of m squared. And that is going to give me 3 square root of x times 3 square root of x is going to give me 9x. Minus the square root of m quantity squared. Again, square root something squared just gives me m. So I'm going to get 9x minus m in my denominator. So my numerator is 6 square root of mx minus 2m all over 9x minus m. So not a very pretty answer per se, but again, there's no radical in my denominator, which is what I wanted. And last but not least, we have rationalizing numerators. So if we want to rewrite a radical expression without the radical in the numerator, we use a process called rationalizing the numerator. And so what we are going to do is just kind of jump into some examples here. It's a very similar process to rationalizing denominators. So for instance, square root of 7 over square root of 45. That is first things first, we want to simplify our radicals if possible. So square root of 7, we can't simplify, but square root of 45, we know divides into 9, which is a perfect square. So we can think about this as 9 times 5. So we know our denominator is going to be 3 square root of 5, and our numerator square root of 7. And then to rationalize the numerator, we multiply the numerator and denominator by square root of 7. So square root of 7 times square root of 7. That's going to give me square root of 49 in my numerator, which will ultimately be 7 and get rid of my radical as I wanted. And then in my denominator, I'm going to have 3 times square root of 5 times square root of 7. So I'm going to get 7 over 3 square root of 35. And as I hoped, the radical is now no longer in my numerator. Next up, we have the cube root of 2x squared over the cube root of 5y. All right, let's take a look at this guy. So the numerator and denominator of this expression are already simplified. There's nothing we can do with the cube root of 2x squared or the cube root of 5y to simplify it more. So in order to rationalize the numerator, we multiply the numerator and denominator by a factor that will make the radicand a perfect cube. So we're looking at the cube root of 2x squared, and we want to get this 2x squared to be a perfect cube. So we need to multiply by something that will get 2 to a perfect cube. So we already kind of talked about this, and we know that 2 times 4 is equal to 8, and 8 is a perfect cube. So we're going to want to multiply by 4. And then x squared to get to a perfect cube, we can multiply by just x, because that will get us to x cubed, and we know that x cubed will have a perfect cube. So if we multiply by the cube root of 4x, we will get the cube root of 8x cubed, which has a perfect cube, which would then eliminate our radical. So we're going to multiply both sides of this by the cube root of 4x. As we talked about in our numerator, we're going to get the cube root of 8x cubed. And then in our denominator, we are going to get the cube root of 20xy. And then the cube root of 8x cubed is 2x over the cube root of 20xy. So again, not a very pretty answer, but my radical is out of the numerator, which is what I wanted. And then finally, let's do the square root of x plus 2 over 5. We multiply the numerator and denominator by the conjugate of our numerator. So that if our numerator is square root of x plus 2, the conjugate is going to be square root of x minus 2, square root of x minus 2. So again, we are going to use that a squared, or a plus b times a minus b equals a squared minus b squared. So we're going to have this equal the square root of x squared minus 2 squared. So, and then our denominator, we're going to have 5 times square root of x minus 2. Square root of x, quantity squared, it's going to be x minus 2 squared is 4. So we'll have x minus 4 times 5 square root of x minus 2. And again, radical out of the numerator, just as we had hoped. So that is rationalizing. If you have any questions, please feel free to drop by tutorial. Math Lab is posted, and have a great day, guys.